because as I was putting up video number 30, I realized that I wasn't going to be able to get everything in a reasonable amount of time. So let's go on with it. Hopefully we can get this one in about 30 minutes or so. So it shouldn't be any surprise that the I'll tell you what, let me back up. Let me tell you what we're going to do here. There's actually about 4 things on the agenda, actually 3 things on the agenda. First thing I want you to show you how to do is to address finding fitted values and the residuals using matrices. The second thing I want to do is introduce something called a hat matrix. And this turns out to be a really important matrix that will not play as big a role right now, but once we get into trying to identify influential observations, it plays a big role. And finally, what I want to do is talk a little bit about the a variance covariance matrix. And this thing's sticking again. So what this allows us to do is it allows us to look at the standard errors for our predictor, in this case B1. Time allowing, I'll get into something called a variance covariance matrix for the residuals. So we'll just, well, I'll add that in the very end if time allows. So guys, let's get some notation down. First of all, I hope you realize now that if I put this notation then I have to add the error term, because this is actually the predicted y that I get when, I'm sorry, it's not the predicted y, it's the observed y. So if you think about the first case, for the ACT and GPA, the first observation was a GPA of 2.4. Now, when we put this in our model, B0, let me look back into my notes and see if I can find that. I think it was, hold on guys, let me, I should have already had that, but I dropped the ball. So 0.648, let's call it. And we have 0.0845. And if we take the x value, which would be the ACT for this particular student, we're going to see that we don't get, we don't have an equality. For example, the left-hand side is 0.648 plus 0.0845 times 18. We get 2.169 on the right-hand side. And the last time that I checked, 2.1649, let me double check that and make sure, 169, not the 4. Those two aren't equal. So what we would have to do is we would have to add the error term to make those equal. Now, consider, I want to get rid of this, use the power of the eraser. Consider, on the other hand, this versus this notation. Now, we don't need the error term there. That's going to bug me. Because what we're doing here is we're getting actually the expected value. So we're putting our x in our model, and we're actually getting this, which I would call the predicted value or the fitted value. Huh, that's interesting. Okay. Now, what I want to examine here is, first of all, let's look at the fitted values. So, guys, we should know that in matrices that we're going to have a response value, response matrix. It's going to be a column vector. So this is a n by 1 column vector, such that you know, we have y hat is x times b. So, building on this, times b0 by 1, again, x theta equal y hat, which leads to this. So guys, when you see that, what you would think is you would think x times beta. So it turns out that you know, we can easily find x beta. So let's just go ahead and do that. So yeah, let me bring R up. Okay, so X matrix, I'm going to save a little time here. And I want to go 1, 18, 1, 22, 1, 25, 1, 28, and 1, 32. And let's go our Y is going to be C of 2.4, 2.2, 2.8, 2.9, and 3.5. All right, so matrix X will have capital. So this will be matrix using X in row equals 5, in column equal 2. by row equals true. So matrix X, exactly what we need. Our beta matrix, let's let it be lowercase. So our beta matrix is going to be, what did we say here? I think I remember, but it's going to really miss that point. So 0.6479. And we get 0.0845. And of course, we'll set up matrix B. Use lowercase b in row equal 2, in column equal 1, by row equal true. So this is exactly what we need here. Now, if we take x times b, you can see what we get here is we get 2.1689. Now let's concentrate on this 2.1689, because when we go back over to the air server, the 2.169, somewhere way back here. Where did I put that? Oh, I erased it, didn't I? So anyway, let's go ahead and say that the predicted value for the first observation, 0.6479. times 18 was precisely, I do believe, 2.169. Oh, sorry about that. All right, hold on a second. Hey, Tanya, will you give me something to drink? Thank you. All right, guys, let's move on into the second thing. And you know, clearly this was easy enough. This should be kind of cool stuff here. Now, let's go into talk about this hat matrix, and we'll be real creative here and call this. Yeah, that's good. Call this matrix H. Now, if you think about what we have so far, we have the y hat is equal to x times beta, and we know that beta can be found by taking x transpose x inverse x transpose y. So if we take this, put it in for b, we will end up with y hat x transpose x inverse x transpose y. Now, if we rethink this as y hat equals this value, and we will call that h times y, we can see obviously, clearly, that h, which is our hat matrix, is x transpose x inverse x transpose and guys, it turns out that this is this is a very important matrix to us. Okay, now this is actually going to turn out to be an n by n matrix. And what it ends up doing is it helps us find influential observations. So I'll tell you what. Let's go calculate the hat matrix back in R. So we're going to do the hat matrix, and I'll tell you what I'm going to do. I'm going to call this matrix Y. And what I want to do right now is I just want to take X transpose times X inverse. So if I go solve transpose X, it's going to just, all this is going to do is just, let's see, so that I can go inverse. Okay, so what I'm going to let here, the part that's inside the parentheses, X transpose times X, and I'll do the inverse of that when I do my multiplication. So I'm going to get a new matrix here, Y. So guys, our hat matrix here will be X times, so I need to go solve Y, because I need the inverse of that, times transpose of X. So guys, our hat matrix, here are these values. Now, I'll tell you what, let's, how much of this do I want to talk about right now? I'll tell you what, let's just leave it at that, that it is easy to calculate the hat matrix, and let's just go back and look at some theory. I'll spring on you a little later what that actually helps us do. Okay. All right, guys. Now let's examine. Let's see how we handle the residuals. And guys, clearly a residual is just denoted by E sub I. And this is the difference in the fitted value and the observed Y and the predicted Y, or the fitted Y. So if we move this into thinking about how this happens with a matrix, there should be no doubt that we're going to take our Y matrix minus our Y hat matrix, which is going to give us Y minus X times our beta matrix. Because back here, remember what we started this crazy thing out with. So guys, to be able to find our residuals, all we would need to be able to do is just find this matrix right here. So this would be Y minus X times beta. And I'm not going to do that. That's simple enough to do with the graphing calculator or otherwise. Now, what I want to turn the attention to now is kind of the third topic. And the third topic here is going to be examining the standard errors. For, in this case, beta 0 and beta 1. And at the end of the day, this starts one of the first steps in looking at the inferential analysis. Now, let's go back to R, and I think way up here, didn't I do, yeah, okay, I'm going to have to come in, let's go ACTs, and let's do the data. I'll tell you what I can do. I can just come up here and copy this. And get rid of the ones. And then let's go GPA. I think I just called that, what, Y? So we'll just let that be Y. All right, good. All right, guys. If we run the linear model, so let's just call this model and linear model for GPA predicted by ACT. And then, of course, we can look at our summary of our model. And what we do is we get our estimates, and we've seen these ad nauseum, 0.647 and 0.0845. And these values are going to be really easy to find out here because remember the t-value is just the estimate, in this case 0.64793 divided by its standard error. And just go ahead and verify that 0.64793, I'll tell you what, let's just do it down here. 0.64793 divided by 0.58554 is indeed 1.107. And just as a reminder, we could find the p-value by taking 2 times p t, and with a t-value of 1.107, the easiest way to do this would be go negative 1.107, comma our degrees of freedom, which would be equal to 4. So we get 0.03. Actually, I'm wrong about that. We have to, hold on, let me think about this. So our t-value is the estimate of 2 things. So I'm sorry. So we got to go 2 times pt negative 1.107 comma 3. And you can see we get the same thing. Again, we have we have sample size of 5, so we have to subtract 2 from our degrees to get our degrees of freedom, because we used estimates for both beta 0 and beta 1 in the calculation of the p-value. All right. So ultimately, you can see that our estimate, our t-value, and the p-value are very easy to find if we know our standard error. Well, guys, it turns out that there's a lot more to the standard error than you may imagine, and that's what I want to go back and give you the indication, or give you the illustration of here. Guys, it turns out that the standard error, which I will call this, of B1, actually it's going to be a B0 and B1, is sigma squared times X transpose X inverse. Now our best estimate of this is the variance, sample variance of B1 equals S squared, which of course we know is, or at least we better know, the mean square error times X transpose X inverse. Now, guys, what we're going to get here is a mean square error is just going to be a number. And the X transpose is going to be, that this will be a, it's going to be, and when we have two predictors, it's going to be a 2 by n. And X is going to be an n by 2. And applying the inverse just doesn't affect what the product is going to be. So we have an n by n. So ultimately, guys, what I'm trying to make here is we're going to end up with a 2 by 2 matrix. So the standard error here is going to end up with a 2 by 2 matrix. Now, what happens here is we call it the variance covariance matrix, because on the diagonals we get the variance that we're looking for the standard error. These values right here actually turn out to be the covariance. So what we're going to end up with, if you think about it, we're going to have B0, B1, and we're going to have B0, B1. So this value right here is going to give us the covariance between B0, B1, and this value right here will give us the covariance between B1 and B0. Obviously, in this situation, we're going to look for the same numbers here. What this actually gives us is it gives us the variance squared, or the standard error squared for B0, and this gives us the standard error squared for B1. So clearly, if we know these values, we can take the square root and get the standard errors. Okay, so let's go do that. And so from before, we know the standard error. So our standard error for B0 is 0.58554. While the standard error for B1 is 0.023. So guys, using what we talked about there, we need the mean square error. And what we should probably do to find the mean square error is, well, the easiest way is going to be to do an ANOVA linear model. I think I called it model, right? Yeah. And we can see that the mean square error is 0.06136. So I'm just going to go ahead and say mean square error is 0.06136. All right? All right. So back to what we did before, we know that the variance covariance matrix for the standard errors of our beta 0, beta 1 can be found by taking the mean square error times. Now we don't have to do the percentage times here because mean square error is not a matrix. It's just a scalar if you think of just a number. And of course, we somewhere up here I think we have x transpose, right? Did I save that anywhere? Thought I did. It could have easily been on the other. Let me see what I've actually got. So I've got matrix X. All right. So I just need to go. I need to go solve. So I can get the inverse of the product of X transpose X. Percentage times percentage X. And of course, the solve part gives me the inverse. Now, guys, what we're going to get here, we're going to get a 2 by 2 matrix. And just like I said before, we expected these values, which is the covariance between beta 1 and beta 0, beta 1. We expected those to be the same. And these values right here give us the standard error for beta 0, standard error squared for beta 0, and the standard error squared for beta 1. So as we can see, if we take the square root of 0.34, 2875, 45, we're going to get 0.5855, which is exactly, well, within rounding, what we expected to get right here. And guys, if you take the square root of 0.00528 9655, you're going to get 0.023, which is the standard error that we expected for beta 1. So the variance covariance matrix that we saw in the previous slide or previous chalkboard, this is where we get our standard errors. So it's really helpful. Actually, it's not more than helpful. It's influential in finding the standard error. I mean, it's influential in finding the test statistic and the p-value. Now, what I want to do now, the final thing, and it looks like I'm going to have time to do this, is just investigate the variance covariance matrix of the residuals. Now, just a little bit of manipulation here. We know, again, in the simplest case, and we know that this can be y minus, this should be hy, right? Let me go back and look at something here. So y minus, so xb, yeah, here. So that can be expressed as hy, which we could re-express like this. Now, you know, back in the old days when, not the old days, the new days, when we're taking like, you know, 2x plus 4, we can just factor the 2 out and get x plus 2. But notice we have to be careful here because the end term, we have to end up with the h on the left side and the y on the right. So this is why I factored out the y this way. So guys, we have that the errors can be found by taking the identity matrix minus the hat matrix times our Y matrix. Now, what this allows us to do is it allows us to assess the variance in our errors. So we have that the variance of our errors is equal to let's see, H, and this will be estimated by I minus H.